This is my own part. And then I need some packages to do this work. So part of the packages are install as differential equation solver. Maybe other ones I use them for something else. And then the XTS is for time series state. So now, because the extension of the file I want to use is CSV, so I need to say read.csv. My file extension is something else, maybe like txt text, read.txt. Because my file extension is CSV, so I say read.csv. So I want to start running so that, yeah, go on. So I'm then running, yeah. Loading. Already I have, so for you, I'm not sure if you have, you don't have this off, you have to come here, go to package, then you click install package. So before you can write require, you have to first come to this package, and then under packages you say install. So it will bring the install platform out, and then you can install. This slow, maybe because of the traffic jam. Or you can use install the package. So and then it will, I think it's coming. So if you don't have the package, you just need to install it. You just type install, then you click install, and you install it with STS. You don't have it, you install it. It will come up now. I don't know why it's slow.
Where do you search it from?
Packages.
So you can use this solve
Yes.
like this, then you have and other ones that you want. You can, if you don't have it, and then I want to run these cases. So you can see the edge. Cases are big. I just want to see the first six rows in the data. So day one, you have 3 cases. Day 2, you have 8 cases. Normally, I can see the data also from here. You can click here on cases. Sorry. Or I can say view cases.
Type it.
You can view the cases here. So, day 1, you see 3 cases, day 2, 8 cases, day 3, 28, day 4, 76 cases, day 5, 122. And you see that it's increasing, you know, until it started dropping again. So now you can use this function view. You'll see to view the cases.
Oh, no.
And then I want to plot. I can plot the cases.
Sir, please can you share the data with us?
The
Data.
I will share it.
Okay, thanks.
So this is the data. This is the graph of the data. So this is not the model. This is just the data for all the days that we recorded so this is the pattern. You can see it's like a common distribution. I started from 0 and then started going up. That's a growth, exponential growth. And then it got to a peak. So the question is, when are we going to get to the peak? So we go to the peak at 300, around 300 cases. And then after 300 cases, the epidemic started going down. Why is the epidemic going down? What do you think? What's the cause? Intervention. What other things do you think can happen when the epidemic is going down? Said people are recovered, and then what other thing? The what?
The rate of infection is going down.
Yes, and they have said this. What other thing? Huh? They have said that intervention. Yeah, it's like the number of susceptible population has reduced. You understand? Susceptible class has reduced. So one thing, when a disease, when there is an epidemic, once there are susceptible population, once we have people who are vulnerable, one of the things that make COVID to thrive, especially in countries where they have people who are agents and have underlying issues, was because COVID was new and then nobody has any immunity to COVID. So the population was susceptible. And then once the population of susceptible are being depleted, then the curve will start going down. And then that's what we saw there. And we find out that it started going down. Now, the going down at times does not mean that this has gone into extinction. So completely. The only thing may be that the speed of spread has reduced. You cannot tell me that COVID has completely been extinct in Nigeria. Okay. But the speed of spread is not, or anywhere in the world, the speed of the spread is not like the initial time. So, now, what do we do? We already, now you can see this, now, if you are going to work on the data, the first thing to do is to do an exploratory analysis. How do I call it? Yeah. And one of the first exploratory analysis is to plot the time series data. Have a time series plot. Look at the behavior of your incidents or prevalence that you want to consider. Look at it. What does it look like? Every graph has its own probability distribution that tends to. So you look at it, and then you can begin to think, okay, since it's looking like this, what are the thoughts coming to your mind in terms of the kind of model that can track this type of shape, this bell shape you are having? So that will be the next thought. Now, how can I capture this dynamics, or sorry, this feature in my model? Because if you don't understand your data, then it means that you don't have a direction for your model. So you need to understand the data very well and try to see what does it look like. Another thing you can do is to do summary statistics. Try to, like this summary statistics, bring the model to summary statistics. What do we mean by that? It's part of the exploratory. You find what's the minimum cases. It's three cases, the minimum. And then you have the median. The median is 73.0. That means at the middle. Now, when they are running Oye-Ekiti, and they want to determine the least mark, most times they don't use mean. Because if it is skewed to one side, it will affect the average. Maybe so many people failed, or so many people passed. So they make use of the median to find, most times, what you call CCs may not be 50.
Yes.
Are you getting what I'm saying now? They have to draw a median statistical exploratory analysis. So for this one, you find that the median is 73. For the average, look at the average there is what? 111. There is a problem there because like the average is changed. So it means that average, what we are going to use to determine this field that is around this. So and then we can look at some other things. That's the average. Sorry. And then the maximum is 293. The maximum case is 293 cases. Understand? So, yeah. Now, we now want to go to the mathematics. We have the equation. This one you have there. I've transferred it here, and I create a function. And the function is this. Function. I called it close notes. You know, like I was teaching you yesterday that variable names. You can use underscore, you can use dots, you can use, but there must not be spaces between each of the variable names. So you have that. And then you see that my function here is a function of t, x, and params. It's different from the other one that I say f of x. So it's a function of x, t, I, x, the variables, and then the parameters. Now I have my x of 1 as the susceptible, I is s2, and r is s3. And then I have the parameters. Parameters are just majorly 2. So if you look at here, you have beta and gamma. And I told you, our data is in what? Is in what unit? Is in what unit? Our data is per day. So it means that this parameter, beta and gamma, they must be per day. Or else there will be conflict. It means that if you don't do that, you're already introducing noise to your work. Now, you have this same one is written in the code R, and then you have the beta minus beta si, which is this, then beta I minus gamma I, which is this, then R is gamma times I, which is this, and then you have the east. So you list and then you close the function. So now we set up a function that will square differences between the observation and the model at any parameterizable sum of square errors, which is this. Now we require this all which you have used, and then I create a function because I want to fit the model to data. So I create a function which is sse.sir, and then function param 0 data. Then I have t is data over 1. Data over 1 in the sense that it talks about each of the days, day 1, day 2, day 3, day 4, day 5, and all that. And cases underscore 1, which is my case data cases. That's why you are having comma 2. And then you have the beta is talking about the beta is 0 index 1, index 2, because the parameter are just 2. If they are 4, it's going to param 0 up to 4. And then I'm setting my initial value for S not to be 762 and I not to be 1. And then, because at that point, at the initial time, there was no recover. Recover will be 0. There is nobody that will recover from the disease. So, and then house as data frame. I have this is concatenation. I want to make my S naught, I naught, and R naught to be listed as a vector of length 3 because they are just 3. If it is up to 10, you have it like that up to 10 listed. So it will give you in form of a vector. And then you have the times. The times is t, and then you have the closed SIR model, which was the first function we used. And then you have the params. The params are the 2 parameters. Yeah. So, and then you have the H max, which is like a kind of discretization, step size, sort of. So, you have this SSE, because you are dealing with sum of square error. Remember the formula, sum, then square, and then we have, now for our model, if you look at it, the only part we are using to compare with data is this. Don't use everything. This is the part we are using for this particular one. This is the one we will plus to compare with the data we have. So the data has said that data said this. So this is the data. And this is the model part we are going to use to fit this model. You don't use everything because this is from here you get the number of cases. So, and then you have that minus cases underscore 1. So you can run, we have not run this, I'm going to run it from the beginning. This is a very simple case, so it's good to start simple and then build the complexities. And then we have for this, we have now let's see how this functions. The flu typically are infectious, and then we have a lot of things around that. So this function works. To start, we'll fix gamma. So if we fix gamma, individual infected with flu typically are infectious roughly 1 day prior to presenting with symptoms. So before they started showing symptoms, they're already infected 1 day before. So in this case, we may suspect that sick individuals were immediately removed. were removed from interacting with susceptible. That was the case with COVID as well. With susceptible individuals, as soon as they were detected and by symptoms. Therefore, for current purposes, we assume gamma is equal to 1, which is G. We fix gamma. What follows? We first create a data frame to contain different parameter combinations and our sum of square errors. And then we use the function sec to generate a sequence of beta values uniformly on a log scale, and the function rep to assign to generate a sequence. Then we use the function rep to generate a sequence, and that's the set of beta values uniformly on a log scale, and the function rep, that is repetition. To each value of beta, the given value uniformly on then we use a log scale and the function rep to each value, and then we do a combination of parameters. So finally we plot the resulting values as a function of beta. So we have this function, SSE.example, and then the data.frame beta, which is equal to this, and then we have gamma fix rep between 1 to 30, and the SSE length not applicable. And then we have for I in 1 dimension SSE.example, which we have given as a function. So we plot the SSE here. We run this function. And then we plot this. So we have this, will vary better, and then so far so good. We can look at our plots and see that there is indeed a local minimum in the sum of square errors. Look at this. There's a local minimum. Specifically, it looks as if the best fit value of beta, the value that minimizes the sum of square error, is around beta equals to 0.03. Around this. So, then we just two problems remain. One, the location of this minimum is not exactly fixed. So it looks like it falls somewhere between the 9th and 11th points. So which is what we are exactly uncertain. So number 2 is that the minimum of this function is only correct for our assumption for gamma, which is equal to 1, is valid. So, but this was only an approximation. Now, for any parameterization you want to do, there must be a starting value. So, if you choose the starting value wrongly, it may take time before you can get your estimate. Now, to solve this problem, we need to one, fit both beta and gamma, and then simultaneously, in which case the sum of square errors is a surface in 2 dimensions, and we are looking for the minimum of this surface, and 2, examine the shape of this minimum over smaller and smaller ranges. So we are going to look at this here until we have zeroed in on the pair. So this process is what we call optimization, right? To optimize. And fortunately, for us, there are robust algorithms that have been built in her, and some of them we use here. So we start with the parameter, we are fitting the 2. So we set one to be 0.01 and then the other to be 0.5 at the initial. And then we run it. So we want to use this initial, this is the initial, our base stuff, and then from there, we move. So you can see it's giving us 0.02 and 0.47 return by opting, and not always the best. So you need to try again. So if you try again, you will see which one. We have done the first one. Let's try again. And see again. And then finally, you can use that. If you compare the 2 together, there will be a little difference. Just little. That little is something. There's a little difference, and then you can plot the beta, the model. Yeah. So the model is in black, beta is in red. So this is the fits, and then we have the estimation. So the estimation for the 2 parameters, what we have there. So I'm going to send the data to us. How do I send? And I send the WhatsApp. Yes. And then you can just begin to run this, you type all this on your own, and then run it yourself, and then you can find. Yeah. So I'm going to. I'll send it to you. I'll send it to Steve. I'll send it to Steve, and then Steve will disseminate. And the code should drop. No, you don't want to type the code. You will make error and then sort yourself out.
So we can send it.
Steve was a different problem.
No. You will be working on the code from there.
What is the problem?
I'll give you the data, and then you will be typing the code, because I don't want the station that you just copy and then run. Let's do this stuff.
Okay.
You type the code from here.
Okay.
I will send you the. So you type it. You will make mistake. You correct yourself. You will run it. You That's very to If I send the code, under 1 minute, you have gone to the graph.
You know what I told?
But you didn't learn anything.
But this is a mistake. This is a mistake. This is a mistake.
You? Yeah. So, science. So you can disseminate it for us. So what you do is that if you have just started working on how, try to create a particular file, maybe on desktop or document for all your house stuff, and then that's where you should put this file. And make sure this file is in CSV, so make sure it remains in CSV. So when you have done that, then you can start this. Now, if you like, I will give you an example now. For my home, look at it. This is where I have my data. You can see. So I can copy the address. No.
Data is not in the.
Are you see? I click on that. I copy the address as text. Yeah. So if I copy it, I put it here. You see? But how does not recognize this directional, this one. See the direction. You have to change it to this part. The part which recognizes this. Right? So this is my own. This is where I put my own. So I will now put this set. I will now put this. Set for directory, and then I go to the edge. I close it. Sorry. I put. Then I close it. So once I do that, I can run it. Okay? So I will try.
The code is not there. You don't have
Which code?
the data. And if you don't have it, send to the WhatsApp. Have you sent it?
There's a general WhatsApp group.
Yes.
I send it to that WhatsApp group.
Let's see.
And then people can download.
What you send it?
Send it.
Okay.
Where is it?